welcome to SanfordFlipMath. We are doing AP Calculus. We are working steadily through the Finney, Demana, Kennedy book for calculus, and we have been focusing on the differential equations chapter. This is our third installment for our 6.1, which is we started out really talking about what differential equations are, equations involving differentials or derivatives. Okay, and on the first installment we really dealt with slope fields, and that's a way to illustrate what the solution to the differential equation, the y equals, would look like. On the last installment we focused mainly on antiderivatives as a way to solve differential equations, and Euler's method is a way to approximate y values from differential equations. It's kind of similar to what we did with Newton's method with finding zeros and using derivatives, using linearization. We use the equation of a line to kind of do that. Well, what Euler's method does, and here's just kind of a quick explanation of what it's about. If you have some equation that's dy dx equals, okay, and so you have some way to find slopes. And this is going to feel very abstract, but I just want you to get a conceptual idea of what it's about. And a starting point. Okay, so I have some starting point. And then if I tell you what the slope is there, much like in slope fields, you can get an idea of what direction it should go. Well, if you take it that direction for a little while and use that to get another point, okay, so now I have another point, and then based on that I find a slope. Okay, so that slope's based off of that y value, and I then extend it to another point. And then from that point, sorry, lots of clicking going on here. From that point, I again use the slope, and I find another slope, and I then extend it using that slope to another point. And then, etc. I can keep kind of inching my way around, and I can get an idea of what the graph looks like, and most importantly, what we can do is use this to find a new y value. So I can start from this y value and use the idea of derivative to kind of inch my way around to get to the new point. Now, obviously, you want to do that in little steps so that your approximations are more correct, more precise, and more importantly, more accurate. So the idea is, maybe the shape of the graph kind of follows that same shape. It's just what we're doing is kind of looking at it in little chunks, little steps, so it looks boxy instead of nice and smooth. Okay, so just to kind of take that. Okay, so Euler's method is again a way to approximate values. It's kind of like Newton's method. Kind of. The goal here is to find y values, not just the x value where y is 0. Okay. All right. So again, just to kind of picture what's going on, here this is a slope field from 6.1a, and I think a different starting point. But again, the idea is if I start at this point, then I use the derivative to go a while, and then I start noticing that as the y values are lower, I'm supposed to get more shallow, less steep. And so, I could go here, and then I could extend, and I could extend, and extend, or I could go this way, and it's supposed to get more steep because that's what this equation's doing. Okay? Well, what I want to do is kind of take that actual equation and do a little bit with Euler's method. Now, this looks a little bit intimidating because there's this big table here, but really what this is for is to help you organize your information. Okay, so here's the concept. We start with a point, xy. We find out what the derivative is, and so and that we're generally told, so here it is, like for here it's 2y. Well, derivative's kind of like slope. So think of it like change in y over change in x. And if I multiply this by a change in x, then what I'm left with is a change in y. So that means I get a new y value by taking the old y value plus the change in y. Well, there was a change in x involved, so that gets me a new x value. So this is that new y value is actually an approximation for the y value for the equation. Okay, so let's actually just do it. And this is how it's actually going to look, and I don't know of any shortcuts to make this work. So you're just going to this is what it looks like. On a test or a quiz, you won't be given this table, so you just have to understand the things that you want to write down. Is the table mandatory? No. Is it helpful? Oh yeah. All right, so I'm going to start at 2,1, and that point was given to me. This derivative was given to me, dy dx equals, okay? So now I'm going to calculate a value for that, and so it's going to be 2 times the y value, so 2 times 1 is 2. Okay, so I'm just calculating, here's my y value, and I'm just calculating the derivative based on that, okay? Now, my goal is to get to 2.4 something. Now, I could go in one shot and do a change of x is 0.4 and just multiply by 0.4, but the problem is that I'm using derivative for a long stretch, and remember that this is really probably a curve, and so it's not supposed to have the same value of the slope for a long period of time. So I really don't want to do that. Really what I want are like little chunks. So instead, I'm going to do 0.1, and I'll just do this a bunch of times. So I'll do 0.1, and then I'll do 0.1 again, and then I'll do 0.1 again until I get down to 2.4 something, or I don't know how many rows it's going to take. We'll see. Okay, I mean, I'm sure we could figure it out. Okay, so this change in x is going to be the same all the way down. Okay, so we'll just be inching our way across. Okay. Okay, now what this next column says is we're going to do the derivative times the change in x. That's this thing. Okay, so the derivative times the change in x. So 2 times 0.1 is 0.2. We got some high-tech math going on here. Okay, now the x value, the new x value, is going to be 2 plus the change in x. So here's my 2, here's the change in x, so this is 2.1. And my new y value is going to be the old y value plus the change in y, so 1.2. Okay? And then we're going to do it again. So I'm just going to write this down again, just so I know that that's what's going on. Now, the derivative is not going to be the same this time. The derivative this time is 2 times y, but it's 2 times this y value. So 2 times 1.2 is 2.4. Okay, so now the new change in y is 2.4 times 0.1, so 0.24. I'm going to add 0.1 to my x value. I'm going to add 0.24 this time, because this is my change in y. 0.24 plus, so this is 1.44. And we'll do it again. Okay, so the more you do this, the faster it's going to go. So I got 2.88 times 0.1. So it'll be 2.3 and whatever 1.44 plus 2.28. 1.728. Okay. One more time, I think. This is 2.3, and by the time I get down to the end of this, it'll be 2.4, and that's my goal. Okay, so the derivative, 2 times 1.728, 3.456, 3456. How cool is that? Sorry, the nerd slipped out, as if I could hide it. Okay, and then we'll add that on to the 1.728, 2.0736. So what is that? This is an approximation for this x value. This is an approximation for the y value. This is not a dy dx, this is y. Okay, this is an approximation for y. Okay, now again, the idea here is this is mostly useful when it's very difficult to analytically find the solution for a differential equation. So you have an equation that gives you differential, the derivative, the slope, and then you just use it to say, I don't need it perfect, I just want a rough idea of what that new y value is. Now, what I want to do is spend just a little bit of time doing this analytically, just so, and I don't remember if I did this in the first video or not, so I'm going to kind of move right along dy dx. The purpose of this video is not really to do this particular problem analytically. We'll spend a lot of time on this style of problem later on in the chapter. but I want to compare. I want to see how close this approximation is. Okay, so I'm going to separate the variables. So dy dx, dy over y equals 2 dx, and we're going to do antiderivative. And again, this is buzzing along. Okay, so don't freak out. Natural log of absolute value of y equals 2x plus c. Now, again, antiderivative of 1 over y is natural log of y, but remember to have the domains work, and together we need absolute value on that y, and that's just an addition that happened from the rules that we already knew. It's just slightly different from what we already knew. Solving this for y, I need to get rid of natural log, so that's log base e. The exponent is 2x plus c equals whatever is the argument for log. And I'm going to flip this around and get rid of the absolute value by doing plus or minus. And this is probably not going to make you comfortable, and I'm sorry about that, but excuse me. Just a reminder that when you are adding in an exponent, you're really multiplying. So here's the idea. If I multiply with two like bases, I can add exponents, and that would recreate that. This is going to probably make you uncomfortable also. This, if I have e to a constant, isn't that just another constant? Whether it was positive or negative, it's still just going to be a constant. So what I'm going to do is rewrite this as a times e to the 2x. Now, one quick little note, remember that we were told at the beginning that it went through that point. You know, it started at 2, 1. F of 2 is 1. Okay? So I'm going to use that point to solve for c. So 1 equals a times e to the 2 times 2. So a is going to be equal to 1 over e to the 4th, which is equal to point, magically changed colors, 0.183 blah blah blah. Okay, so that means that y should be equal to 0.0183, or you could just leave it e to the negative 4 if you want, times e to the 2x. Now what I want to do is find out what f of 2 is. Okay, so I'm just going to put in 2 right there for x. Okay, so times e to the 4th, because 2 times 2 is 4. Okay, really? Okay. All right, and that ends up being 1. Now that's pretty darn amazing. Now, probably worth noting that I left the complete decimal in the calculator. If I type this in just to that rounded value, it ends up instead 0.999146. That is funny. Now, why did I bother to do that? I really wanted to. That's funny. And now it's recorded, and I'm not reshooting the whole thing. Sorry. What I really wanted to do was f of 2.4. So put 2.4 in there. Okay, that was clever, Mr. Sanford. All right, where am I? There I am. Times e to the 2.4. I thought, wow, that looks really clean. Why is that? All right, here we go. 0.20189. Okay, now I don't understand what's going on. All right, I got it. I typed it in wrong. This is really supposed to be, okay, so when I put in the 2.4, this is supposed to be e to the 4.8 power. Okay, so this is the 0.0183 e to the 2 times 2.4. Okay, sorry, that was a long excursion, and this ends up 2.2255. Now, what I got was this, and it's not the same, right? But do understand that it's not the same. It's an approximation, okay? And that's just going to have to be okay. All right, let's do this one more time, and that should be plenty, and we'll call it good. All right, so what are we going to do? We're going to start with the point we know. Okay, that's this. And then this is 2x minus y. Okay, so we're going to use that to find derivative values. Okay, so 2 times 1 minus 0. Okay, so 2 times 1 is 2, so that's 2. Okay, we will be multiplying. Again, now normally it's going to say use an increment of something, and so I'm just going to tell you that we're going to use 0.1 for this, and that's probably a pretty common value for what we're going to be using, you know, even in the homework. So 0.2, and now this is going to be 1 plus 0.1 and 0 plus 0.2. So we're going to now use this point. So now it's just repetition at this point from here on out, okay? So 2 times 1.1 minus 0.2. So this is 2 again. Wow, that's really weird. Came out 2 the same answer. So just a quick, I just want to double check. 2 times 1.1 is 2.2 minus 0.2 is 2 again. Okay. I don't know that that will keep doing this. So this will be 1.2, excuse me. We added another 0.1 on. And then 0.2, so we'll add that on, 0.4. Okay. All right, so here we go again. 1.2, and we're going to go 4. Okay. So 2 times 1.2, 2.4, minus the y value. Oh, that's really weird. I did not expect that at all. That's cool. 0.2. I know you guys are sitting there going, yeah, it's not that exciting, Mr. Sanford, come on. And then 0.4 plus 0.2 is 0.6. All right, and we wanted an approximation, and there it is, so approximately 0.6. Okay. Okay, well, the process is pretty much the same from here on out. You know, there's not a point to doing like 1,000 examples of this, but here I would practice building this table and you know, do it a couple of times, maybe come back and do another example. Again, you know, we could try and do this analytically and see how close we actually got. I'm not gonna, and we're just gonna leave it at that. So another video under 20 minutes. I'm quite excited, and thanks for watching. This is SanfordFlipMath, and sayonara.